мы видим, что, значит, получается...
Экран видим хорошо. Слышно, да? Да, все в порядке.
Я могу и по-английски, а могу по-русски, как удобно.
Как вам удобно? Нам все равно. А что у вас там в аудитории? У вас там есть один иностранец, нет?
Okay, let's try to do it in English. No, it's absolutely okay. It's okay, yes. Good.
This talks. Okay, we start our seminar today. We will have speaker from Skoltech, Anvar Baimuratov, who will present result about Moiré systems.
Yes.
So, floor is yours.
Thank you very much for very nice introduction. And yes, today I will try to tell you at least about one story about exciton-polaritons in Moiré systems. And if we will have time, I will present special topic for Vova about reconstruction. But if I don't know what about time limit, but yes, and let's see if we have enough time, I can show additional. As I know, here you are professional in polaritonics, in all polaritons, and I will show you. No. Okay. I will show you one story what we did, and it would be, let's say, experimental part done by my colleagues in LMU, and I just did a small model for this, and maybe it would be interesting result for your community. It is about Moiré system, and I will introduce. Okay, good. I will introduce very fast late materials. We know that we're quite famous now, graphene. We can take not only graphene, but we can use transition metal dichalcogenides for semiconductors. We can use HBM for insulator. And now we have many new materials that people study, like magnetic material with chromium. We did some work also on this chromium-suitable brom, CRSBR material. But today I will talk only about TMD systems and heterostructures based on TMD. Good. TMD, you know probably, but very fast, it's not like graphene. We have three atoms, like width of three atoms. We have one transition metal and two alkagenides. You can use for, let's say, for optics, this 5 combination, and this 5 combination will have band gap around 1 to 2 electron volt, and they have direct gap at K points, and most of the talk it will be about exciton physics. Why excitons are good in such system? Because they have huge binding energy. It was especially huge in the beginning. It was started from, I would say, 500 or more MeV. And now I think it's stabilized around 100 to 200 MeV. And I believe true is more like 1 to 200.
So it's less.
Calculation, I mean, DFT calculation, it was in the beginning, and the first work, I believe it was also maybe Chernikov, he did his estimation, and it was at least like 400, I think, yes. And the DFT in the beginning was very bad.
That is also because now they are most of them are encapsulated and here it screens a lot that are interaction, while previously if you're freestanding or at least on the top it was a year. So
yes, maybe it's partially, but I believe if you screen, you have two effects probably. One increasing change of the band gap and change of Biden. Usually we compensate a bit, but in any case, now I believe it's 100 or 200 MeV. And we will look to the optics of these materials. And okay, yes, I understood. We will study heterostructures. Again, as discussed already, we have usually two layers. It would be heterostructure, and it is encapsulated in HBN. Also, we can put some layers of graphene and use them as gates. Yes, and this is why we can do two things mainly. We can apply electric field or inject electrons or hole to our semiconductor. And famous Moiré picture that you can take two layers even and twist them. And twist, it's a new degree of freedom that you can use. And we will see formation of the super lattice in such system. And usually we think about such superlattice like Moiré period, new period will be much larger than initial period of the monolayer. Yes, and this is why we all of us we can use all continuum models, and we can introduce local stacking and introduce kind of local symmetry. People also talk about local band structure and band gap, but yes, idea that you have, do you see, all of us see, yes, point. We have here, for example, we have hole over hole, and in some place we have atom over hole of the hexagon, yes? And this, what I will call local stacking in such system. You can create this not only by twist, just by taking two different layers with different lattice parameters. And this was geometry. Okay, yes. Yes.
It was much will be large and more will be very small. So
yes. And you cannot easily introduce local stacking, and you cannot use
period of layers.
And continuum models will work very bad. Yes, and here what I will use, like idea that not only with stacking, not geometry, it's not only geometry, but also you can introduce periodic modulation of potential for electron holes, and I will introduce it mostly for excitons. Like everything would be mostly an excitonic picture, and excitonic effective Moiré potential. And such potential can be large enough to effectively localize. It can be, again, like around 100 MeV, sometimes smaller, but it's enough to localize excitons and localize also charges like holes and electrons. Good. Here you see maybe just idea of these continuum models, because yes.
For example, confinement potential for electrons separately and hole separately.
It depends.
Yes, they can be in different places. I will show a model where I just summarize them and talk about only confinement potential for excitons. But you're right, they can be at the same high symmetry point localization and can be in different high symmetry point. It depends on the material. Yes.
This is important. This point of maybe in the reciprocal field.
Yes, yes, yes. In real space localization. Good. And yes, I will talk about, let's say, some of this and show some results what we can do. And usually, if we believe in this continuum model, we can introduce Law's expansion in Fourier space, like you have just first harmonics, and this is why it's if everything changes smoothly, all the stacking changes smoothly, you can use this low harmonic expansion as usual. And now I go to details. We have heterostructure. First layer will be molybdenum diselenide. Second layer would be tungsten disulfide. We have largest mismatch of 4%. It's not so large. I believe maybe 10%. It's already large, but 4 it's not too large. And here you see DFT calculation. And from this DFT calculation, we know that in such structure, we have resonance of conduction bands, and we know that holes all the time they sit in moly layer. Yes, you have holes here. This is the top valence band. This is the bottom conduction bands. And you see conduction bands are in resonance, and for this heterostructure, holes they will sit in moly layer. Moly, it will be molybdenum. What?
The colors.
One of them is TFT, and second one is JW. And yes, but result, I would say, approximately the same, like we're in resonance in both cases, approximately. And one work, we just try to understand what are the, is it type 1 or type 2 heterostructure? And for that reason, we built this system. As I said, we have heterostructure, insulators from both sides, and we can apply voltage. In this case, we study this system, we apply electric field perpendicular to layers and fit the model. As I said, we took that potential for exciton, and by fitting these parameters of this potential like we took data from experiment and fit all the parameters for the model and found that we have 3 excitons. These are absorption from experiment and from theory, and we have 3 excitonic peaks that absorb, at least first 2 absorb large enough to see them in the system, and we have 3rd peak. And we call them M1, M2, and M3. And what is important, what was our what we found, that all these 3 peaks, they localize in different high symmetry stackings. Like M1 will be, this is Moiré unit cell, and here we will have localization of M1, here we will have localization of M2, and M3 it would be in the...
As this peaks from interlayer excitons, we will assume that
okay, in that paper, we found position of interlayers. These 2, M1 and M2, they are interlayer peaks, and M3, it's actually doublet. If you look for 0 voltage, it's like anti-crossing here. Like we found positions of interlayer peaks, because if you apply electric field, they will have slope in this portion, yes, because of the permanent dipole moment. And we found this anti-crossing. And M3, this part, it will be hybrid.
But these lines show change in energy in electric field.
Yes.
And what is the value of dipole moments for these lines?
It's just kind of distance between layers and
Layers.
yes. We just took
Stretch, for me, because if you say that there is resonant hybridization between conduction
yes.
states, therefore conduction state is leaves well, let's say 50-50 on two layers.
Here, yes, but here for zero electric field, it will be a fully intralayer, maybe with negligible percent of.
Understand there is also charge injection, right? So there is
It will be
required-
later in the talk. Now I just show you what are the, let's say, real space position of first, at least remember first two M1 and they idea that they localize in different high symmetry stackings.
What about the details of theory? How is that?
What?
How about the theory? How you calculate it?
Okay. Here maybe I will show you just briefly. It's you have expansion of the potential. It's just, let's say, this 6 vectors. Yes, you have, and at the end you have two parameters. You have amplitude of this potential and phase. Phase control kind of shape of the potential, and phase changes. Let's say what would be the minimum, where would be the minimum, at which point you have a minimum potential energy. Yes, and you can create two equal minimums or create only one big minimum. And here it was fitted, and it's only with, let's say, some parts of the parameters you can find this series of excitonic peaks. Yes, to get this type of the absorption, we fit amplitude here of these peaks. For interlayer peak, we just found this anti-crossing, and yes, it's also parameterized by, let's say, tunneling amplitude and phase. But usually it's important to fix just phase in one of the parameters, like in Moiré potential or tunneling between layers. But yeah, here you can see now what would be the, we have again, this would be next part. We have this Moiré unit cell again, and we know positions where we have this M1 and M2. And you see the cross-section of the potential. Yes, first would be in the minimum of the absolute minimum, and second would be in the second minimum, M1, M2. What is important that we also know that this M1 high symmetry for M1, it will be also the minimum for localization of the electrons. Let's say electron will have approximately same profile for potential, and this is why M1 and electron that you inject to the system, they will be localized with M1s. And what can we do? We can start to inject electrons to system, and because of this Moiré potential, you will actually feel only these minimums at first. Yes, and you can, in principle, think about these Hubbard models when you have bands. Yes, and you start to feel this band, and we can introduce something like number of electrons per Moiré unit cell. And what I will be talking in next slides, it is a filling factor of 1 electron per Moiré unit cell. In principle, you can dope and you can get all the fractional fillings, I don't know, 1/2, 1/3, and all other possibilities, but we will talk about situation when we fill, at least we believe, we fill each Moiré unit cell with electron. and it will be at this position. This and yes, and now we also can put this system to the cavity, and we can study different parts of this polariton physics.
So that you believe that you will get array of localized random states or
I can say on this picture, this is doping diagonal. Yes, here we have 0 electrons. Yes, here we have 1 electron per Moiré cell. And you see what happens. This is very important question. Behavior of these two excitons, they start to be very different, because M1, it looks like it, you see, we dope, and we start to see trine. And energy of this, binding energy of this trine, approximately same as in monolayer. And it's obvious because they just localize at the same point, yes? And this is why we have here for M1 trine, we have step in energy. And behavior very similar to monolayer trines. But for M2, situation is completely different, because we have, let's say, electrons and like lattice of electrons, and delocalize from this lattice, M2. And you see that M2 now, it does not show this abrupt step. It just slightly changing in the energy. And we, like in the beginning, we call them, I don't know, remote trine or something, but maybe M1 minus, it's good trine, and second one, it's something like complex lattice, electron lattice plus exciton. Maybe it's better to call it like this, I would say. It's good. Second, it depends. First, you can start to dope also to tungsten layer. It depends on the system. What?
Holes.
No, for holes.
You mean electron? Okay.
Yes, you can also dope to the M2 position, and at one moment, maybe even here, you see, at one moment this guy disappear, and we see, let's say, normal localized trine, monolayer type trine again. And this is the sign that we dope at least 2 electrons per Moiré unit cell. But now it's, let's say, we don't care about fractional fillings. We think about two situations. We have 0 electrons per Moiré unit cell and 1. And this is why we call it like triangular lattice of electrons. Moreover, people put that from our group and from Schneider group, they put this system to cavity, and we also can apply magnetic field. It's, as I understood, it's not so simple, but I think only now, I think in Schneider group, we have possibility to put everything to cavity and also measure with magnetic field. And we can change cavity length, yes, and in principle, we are in a strong coupling regime for this cavity. And we can measure Rabi splitting, and we can measure it for what we call M1 and M2 minus. We can measure for everything, but here you see only for M1 orange points and for M2 minus. Okay. Yes.
This experiment, when you have 0 gate voltage, you have coupling of excitons with cavity modes. And then when you have filling factor 1, you have coupling of M1 of M1.
this is also later track.
It loses, yes, you have this repulsive polaron or trion, and all the oscillator strength goes to the M1 minus here. Like at one moment, it disappears completely.
And it started to be off resonant with cavity mode. Why?
No, it loses completely oscillator strength. Yes, and it happens even in monolayer. Like you dope, and your trion start to get oscillator strength, and your exciton part or repulsive polaron it start to disappear. Yes.
Horizontal dashed lines is the strong coupling condition. No, the last.
This I don't remember. This I don't remember. I will not say.
And both these states are optically active in the sense that electron and hole are not separated in space, right?
Yes, they are mostly localized in molybdenum diselenide layer. Yes.
Because there are other states, but as a two-level bi-layer systems. But
yes. If like M3 was good candidate for this hybrid, yes. Kind of here you will have 50-50.
Mm-hmm.
But it's also, let's say we assume that we assume only excitonic picture, but in principle, there are special type of, I think people call it like charge exciton, when you have also heterostructure, and even in if they can be in one layer, yes, they electron and hole can be delocalized. Yes. Like you can have delocalization not only in Z for exciton, but also in XY plane. This is what I want to say. But here we don't have these complications. We have everything in one layer, and we believe that we localize enough that we are optically active, and we have enough overlap of electron and hole. Good. Second part of this kind of category, that we can also apply magnetic field, and we can measure Zeeman splitting, and this is just the dimensionless measure of, let's say, how your two excitons in K plus and K minus they will split. Yes, and G, it would be just dimensionless kind of measure of Zeeman effect. We assume only linear effects, only linear term to the magnetic field. And what is good, and maybe most of you know, that because of special circular polarization selection rule, in one K point you will have sigma plus, and the second point you will have sigma minus exciton that will absorb or emit light with this polarization. And usually experimentally you excite with linear polarization, apply magnetic field. Yes, you split these two excitons, and easy to measure one polarization and second polarization separately, and just measure this difference. Yes. No? Okay, it was just a brief explanation. Yes, maybe. And now we go to our M1 and M2 exciton, and we can measure this Zeeman splitting, measure G factor. Here you see again these two situations. We have we don't have any electrons in the system, and for second situation we have these electrons. Yes, and first we look to the M1, and for M1 we measured this G factor of -4. It's very similar to monolayer type, and let's say this localization does not change something sufficiently. And here when we measure G factor of M2 minus, we have G factor for this M2 minus, we have G factor of -30. And this happens because now we have additional part for G factor that has this electron lattice, yes? And when you apply magnetic field, for small magnetic field, first you polarize your electrons, you have spin polarization, and you have a magnetization of your lattice of electrons. Yes, it's effectively just additional magnetic field for small fields. And here, yes, yes.
Electrons in conduction band of particular material have specific G factor, which should be close to -4. Why? How do they contribute -30? You polarize electrons, free electrons. Free electrons in band theory have, I mean, not free, but band electrons have particular G factor.
Yes, but I mean, idea that if it's also in this kind of effect, but it's, let's say, it will show you how your electrons will, how they polarize fast or slower. Yes, but in any case, they introduce additional magnetic field. Now, let's say M2 surrounded by polarized spin lattice. Yes.
Hold on, is it all in the cavity or bare excitons?
Now, first I show without cavity. Next, step by step, I just show it, just to show separately effect that you can look. Yes, good comment.
For M1 minus trial peaks, how you interpret that?
It's same as monolayer. One is just disappear because you have everything in like you change position of conduction bands. You put electrons only to one value, and that's it. And you can create only one polarization of M. Like you have only one polarization. It's pure monolayer effect. This is why I'm not showing you kind of this part. You see it just disappear. Yes, blue kind of zero. Here it's everything is like 4, -4. And you have question or what? No? Okay.
But actually, the blue peak is higher. It means that
Uh,
the
it-
oscillator strength is also redistributed.
Yes, yes. This is interesting. Now we look to this M2, which is not trivial as, let's say, monolayer type excitons. Now we look to this complex electrons plus exciton, and for small magnetic fields, we at one moment we fully polarize all the electrons, and we have again G factor of -4. Yes, but we look just for this linear slope for small magnetic fields. And this is why we see increase of this G factor. But second part, as you said, we can look to MCD, or it just area under these peaks. And you're correct that now this sigma minus polarization is larger than sigma plus. And we phenomenologically just introduce oscillator strength. This is relative oscillator strength. And I introduced effective G factor for this. Let's say we measure this slope for small magnetic fields, and it changes. Yes.
I think a similar effect was observed in Sheffield, and the theory was done by Guillaume Malpeche and Dima Solnschka. They called it giant G factor, but it was in the cavity, so maybe it was different.
This G factor for oscillator strength, and I just introduced it phenomenologically that it changes. It changes just because of presence of electrons.
Yes,
Yes.
and I think they had the same interpretation because they polarized free electrons that redistributed the oscillator strength between the two spins, and then because only one only one spin component was coupled to the cavity mode, that created an effective giant G factor in the cavity. But maybe so far, if it's not in the cavity,
I will show you changes in G factor on next slide. But now we know that oscillator strength also depends on magnetic field. Yes. This fact I use, and I introduce this kind of effective G factor for oscillator strength. And now we go to cavity. Now we have cavity, and we.
Does it correspond to also, I mean, G factor in terms of -30, which you, and G factor phenomenological G factor.
Let's say one effect, if it's just magnetization, yes, of they must be coupled. I mean, oscillator strength, I think we don't know exact microscopic picture of change oscillator strength, but we definitely must be somehow coupled.
Well, if it's at high temperatures, then
in the value, you know,
it's 4 Kelvin.
you know, -30 there, and
No, it will be not
even
minus.
most, if you split the two,
I will show you how. I will show you values.
if you split two energy levels in energy, then it's low temperature. You will also redistribute and polarize electrons, and that obviously means redistribution of oscillator strengths. So it makes sense microscopically.
Yes, you have you just change effectively overlap of electron and hole, I believe. Yes, yes. But exact, let's say, numbers of these exchange properties we don't know. We phenomenologically introduce these two, and now we can also look to the cavity, and because we change oscillator strength for sigma plus and sigma minus exciton, we also change Rabi split. Here introduce very simple model. Yes, we have sigma plus excitons, sigma minus excitons, and we can introduce two like branches. But now we have, let's say, we also have magnetic field, and not only excitonic part has G factor. Yes, like not the eigenenergy of excitons will be dependent on the magnetic field. This is just simple Zeeman effect for exciton, but also Rabi splitting will be dependent on magnetic field. And here you see you can introduce directly G factor for G factor for Rabi splitting. And here it's dimensionless, it's good. And this G factor for Rabi splitting and for oscillator strength, they have this connection.
This without gating field, only with exciton, right?
This is with gates and for M2 minus situation.
Such that currents are dominant. Right?
No. We look to this. We look now to this exciton with for filling factor of 1 and magnetic field and cavity. Okay, polariton. Yes. I need to switch to I am not. Now I will call them polaritons. Now we have branches, but I just described that effect of magnetic field comes here not only from excitons but also from Rabi splitting. We introduce different Rabi splitting for plus and for minus, and we can connect them with G factor of oscillator strength. And here we just did separate experiment. Without cavity, we can measure effect for oscillator strength, and we measure Rabi splitting, and here formula is correct.
Splitting scales linearly. Magnetic field. Did you calculate it, or you just define it?
Yes, we just introduce it, and we don't, as I said, we don't know microscopic calculation for that. If you're interested, welcome. We can. I know your work, and but here effect will be not the same. Yes, because you have electron lattice, and this is this what changes kind of sigma plus and sigma minus. And let's say filling bands little bit different kind of. Let's say at one you have already filled band or half filled, how you define. Yes, and let's say main result that now you can calculate G factors, and we can introduce different parameters, like we can do like three things, let's say. We can have, again, 0 G factor for Rabi splitting, and here you have detuning, yes, from cavity. This is delta, and you see this would happen if you don't have any effects for any effects of magnetic field on Rabi splitting. It's just symmetric. One of the branch take kind of G factor from excitons, and at the end it goes to 0 because we don't have any G factor for photons, and just mirrored for another branch. But here, when you have this G factor for Rabi splitting, depending on the sign, you can, in principle, for different sides of the detuning, you can effectively increase amplitude of this G factor, and in principle, you even can change, let's say, effectively G factor for branches. Yes, because let's say nothing was initially positive, no positive G factor, but because of this connection, you can have because G factor of exciton was -30, but now you can have positive G factors in your system. And let's say it's one of the way how you can, by detuning, you can control G factor in this system. Here you see the final formula for this G, for these two branches. Do you see? Here. Well, yes, and it's easy to get. And if you assume that G factor of exciton much larger than this G factor from Rabi splitting, you can even find like values how you can effectively increase your G factor, or how you can get this positive, like it's just minimum and maximum here. Yes, it's like what is the maximum for this effect. It's just with this assumption. And this is the experiment. And you see, first when for our M1 without any electrons, everything is symmetric. Yes, and if you go to this electron lattice plus exciton for M2 minus, we observe first asymmetry for detuning, and we even measured these positive G factors for our system. Yes, it's like one more effect that you can introduce to this cavity plus Moiré polaritons. Okay, I don't know about, like, do you want to listen conclusions, but let's say we found this system, we measure this Moiré polaritons in presence of electron lattices, and let's say introduce this phenomenological model for G factors for this system. Questions for this part?
Of course, I missed main part, but I noticed that you don't have any mixing between spin up and spin down components for either optical mode or excitons. And intuitively in Moiré structures, you would guess that there is some anisotropy in plane, and it should create kind of effective spin orbit interaction, mixing sigma plus and sigma minus modes.
I think it's it's not so large effect with all this mixture. It's like not so large, I would say. These effects are much larger. With that mix, it's like 1 MEV or something for monolayers. And I believe for our Moiré system, it's in order of that values. Let's say, yes, they can be connected, but in this work, we neglect this effect. Okay, if we don't have questions for this part, I can very fast show.
Still have 15 minutes.
Okay, I will show second part about reconstruction. We have here a professional of reconstruction, and it was his question to me to show it. I will show it. I believe you know some parts of that you can introduce domains in these Moiré systems. When you have very small lattice mismatch, it will be very effective. And here we choose a system where lattice mismatch was very small. It was tungsten diselenide, molybdenum diselenide. Mismatch is less than 1%. And again, we can introduce this interlayer energy, GSFE or adhesion energy. Here we'll call it GSFE because I calculate them from 0, but it doesn't matter. And here you see that some of the stackings they will be yes. And you can calculate this adhesion energy, and you can find that some of the stackings they are optimal or more optimal. This happens first for graphene, and in transition metal dihydrogennates you can do absolutely the same, calculate this energy. And here we will have something like called 0 degree stacking or R stackings. And we have two optimal stacking. Let's call them AB or BA, many different notations. And you see what happened when you start to optimize your lattice. You have two terms. You have strain energy and you have interlayer energy. You optimize this problem, and if you do everything correctly, you will observe that you have very large domains. Yes, and for smaller angles, domains they will be larger, and the effect, let's say, of reconstruction will be very dramatic. Okay, and here I show some bilayer graphene and possible, let's say, sometimes it's really periodic, but in reality it's not all the time. And in one of our work, we study this type of heterostructure. And for this heterostructure, it's type 2 heterostructure, and all the optics, let's say low energy optics, will be depend only on interlayer excitons. When hole sits in one layer, electron sits in other layer. And we study the possibility of initial strain manipulation that you can, let's say, build in with some initial strain. You can create some patterns that can be used for some application maybe. And idea of the work was, is it possible to introduce special strain to system to obtain 1D wires on purpose? And we successfully did that. We used this large, let's say, relatively periodic Moiré system. And you see here that it's quite periodic. And we took this heterostructure. It's also was with HBN, and we put them between two gold bars and introduce strain to system. And we calculate that, let's say, if we use this, if we have this strain, this reconstruction picture will be less optimal than this. Yes, the system start to be from this kind of 2D triangular lattice, it start to be 1D super lattice or 1D wires. And what happens? We have here two optimal stackings. That's called green and orange. But because these are not homobile layers, optimality of these stackings, it's we have very small difference, like around 1 MeV per cell or something like that. It's you need to introduce very small difference to these stackings, and when you can get this double domain wall, and let's say one of them will be here green stacking, yes, this here again green, and between these two domain walls you will have orange stacking, like shown here. Yes, it's one of the wire. And it's good because, let's say, it's one of the first step how you can manipulate on this reconstruction on purpose. Let's say this was very simple geometry of these two gold bars, but idea that you can create more complicated patterns and maybe introduce not only wires, but maybe some connection between these wires and other interesting things. And we prove it not only with some electron microscopy, but also why we decided to use this system. Because we know in previous work we calculate energies, and we know from experiment energies for these two stackings, for green stacking and for orange stacking. And we know that the difference between, in excitonic picture, the difference between these two excitons will be around 120 MeV. And this double double domain wall here, you will have one domain wall here, one domain wall here, and effectively it gives you just sufficient localization for excitons, of interlayer excitons. And if you measure optics for this system, you will see linear polarized photoluminescence. We observe splitting, yes, and the splitting here was around 1 MeV, and because of low temperature, we see only one polarization, linear polarization for our excitons, and they just polarized along the wires.
Wait, main double domain works on this C picture or B. Is it no? The place it should be.
B?
I mean,
Here.
you show so on my on panel C, no. On panel C, you have map here. Is resolution of polarization.
Yes, yes, it's just linear polarization from very large. This is, I think, maybe 10 micron, this bar, and this is
how oriented with respect to this.
they oriented.
Is it known?
Yes, yes, they oriented like this. Yes, like from perpendicular to these bars. Yes, like yes, like here. Here it's an easy version of your question, answer for your question. Good. Yes, and we had possibility to measure many samples, and we found that we have actually we introduce distance between these two walls, and it depends on angle. You see that it started around from 5 to 15 nanometers, and in principle you can change your confinement, and we prove that. we found that for, let's say, smaller width of this wire, like here, we have larger energy, and it's approximately, if you just calculate this fit, it's just the infinite potential barrier, like infinite potential well, and model works nicely. You can change energies, you can change distance between these wires, and here some simulations. And yes, as I said, we need to introduce small difference between these stackings for interlay energy or for this adhesion energy, and only in this case you can observe this special type, I would say, of double domain wall. Yes, it will be, if there is no delta, everything would be like half green, half orange, but because of small difference here, we have this only small part of this orange stacking. And we luckily have this, for this we also have confinement for interlay excitons that we can prove that it also from spectroscopy will be exactly like, let's say, quantum wire. Here you see profiles for different angles. This is the adhesion energy or interlay energy, and here you see just deformation field and strain tensor. Okay, I think this was the last slide. Questions?
So for the previous part, are we allowed to?
Yes, absolutely.
Maybe I ask about is it possible to make contact to this straight segments of the sample where the angle is straight and measure transport?
I think it's possible. We mostly doing, like in LMU experimenters, we're doing mostly optics, but yes, I think it would be very nice to check all these transport properties. Yes.
Yeah.
Yes, but yeah, maybe next steps. We just sent this paper, like we're waiting for reviews, but yes. Next steps, definitely we can try to measure transport. Like what I want to do, like to understand, let's say, how far we can go from these simple wires. Yes, what is the geometry that we need to introduce for these gold bars that we can obtain more complicated things than just wires. Yes.
Yeah.
Let's go.
So I actually Googled it. The similar Google what? Good question. My question, yes. A similar effect was observed in 2022 Nature Photonics Lines first author in Sheffield, and they called it giant effective Zeeman splitting in monolayer due to spin selective strong like matter coupling. So essentially they did a similar.
But no more.
No more.
In our system, it's, as I said, it's a different effect.
Sure, but I would say that conceptually it is somewhat similar because you essentially suppress the oscillator strands of one spin component by polarizing electrons, and then because you suppress spin oscillator strands, you also suppress Rabi splitting and giantly amplify the Zeeman splitting because of this coupling to photonic mode, right? Is it? Or did I misunderstand?
It is not the same.
Yes.
It's the same deal for M
Yes.
minus tri, but
Yes.
he is given with M. If you show the spectrum, the previous one. You know this one.
Okay.
What you say is this about M1 minus. So this is the
Yes.
effect.
Yes, this is giant effect. You see effect that one polarization just disappears.
Yeah.
For the other one, he is
Yes.
dealing with minus.
It's moreover opposite if you think about effect.
Why is it? case.
Because in one case, you just fulfill only one value, yes, K plus or K minus, yes? And you cannot create one type of trions.
Yeah.
And this is a giant effect, kind of, yes. And here is, let's say, because overlap of these electrons, it's not so large, and it just, let's say, you can think about, like, you have, let's say, spin, like lattice, yes, here, and M1 is surrounded by this spin lattice, yes? And in one case, you have, for example, if here you have spin up, yes, all the electrons will be polarized spin up, yes?
Yeah.
And you have two types of excitons.
Yeah.
And in this exciton, one of the, like in one case, for example, electron will be spin up, and in second case, it would be spin down, yes? Maybe hole also important. And we don't know exactly what would be exchange here between this let's say, lattice and exciton. This would be important for this oscillators. And I believe that something happens with exciton function, and overlap of electron and hole will be different for these two situations.
Okay.
But how to calculate that exactly, we didn't do that.
It's interesting. Okay.
But yeah, maybe if you're interested, we can try to like find way how to get numbers more correctly, because here I just introduced terminology.
But in the end, phenomenology, well, you still have giant amplification of the G factor, right? So third.
Yes, even without cavity. Yes, this happens. But
I have
yes,
what to understand. This minus 31 appears because when we polarize your electrons, they create some effective.
yes, you do the magnetization, yes, and they create effective.
And this thing is just because when you have minus negative G factor, so this effective field how to say, helps to polarize.
Yes, it kind of interfere constructively, but
Yeah.
you have different you can do different things. If you, as I remember, you can get positive G factor if, for example, you inject holes to your system.
Okay.
And in this case, it's really this amplification, and is it destructive or constructive? It depends of G factor of these charges.
Yeah,
Yes.
exactly. Yeah.
Yes, an effective field, let's say direction of effective field.
Thanks.
Yes.
So, do you have another question? In Zoom, Misha. Oh.
Нет, я всем доволен. I have no questions, thank you. It's a lot of more.
Now we let's as a tradition, we give you sign of because
Thank you.
So the next one,
next we don't know still, but today we say something.
We have three candidates, right?
Three, yeah, three in the game.
Спасибо.
да, здравствуйте. Я был в административных делах, поэтому